Now let's think about another topic, which is total reflection and near field. And probably many of you don't know the near field, so let's check this out. And now what we are thinking about is the light irradiation from one side, and it is reflected at some interface. And this interface is defined by the different refractive index medium. So in this case, the higher refractive index side, the light is irradiated from the higher refractive index side, and the lower refractive index side is in the bottom. So this light field is reflected here as the X plane. So first, let's review the Snell's law, so which is sine theta 1 over sine theta 2 equal N2 over N1. Right. So as you know that, I have to mention, so many of you know that if the light is irradiated from the higher refractive index side, as the light is totally refracted at some angle, larger than some angle, which can be understood by the Snell's law, because in this case, the N2 is larger than, N2 is smaller than N1. That's why the angle of the incident angle is always smaller than this theta 2. But if you keep increasing this angle, at some moment theta 2 approach to the pi over 2, and then there's no other way to go. So that means this condition is satisfied by in the case of total refraction. So theta 2 equal pi over 2, meaning the sine theta 2 equal 1, and then theta 1 can be written like, so sine theta 1 equal N2 over N1, meaning theta 1 equal sine N2 over N1. So at some moment, so when the incident angle is larger than theta 1, the light is totally refracted. And now we are thinking about the electric field for the incident light, and the transmitted light, so E and E prime. Now we assume that the wave vector of this one is k, and this wave vector is k prime. And then you can write the E of x, y equal E0 exponential. We neglect the time dependence, k or equal 0 N1k, which is a wave vector of the in vacuum, and sine theta 1x plus cosine theta 1y. And similarly, the E prime prime xy equal E0 exponential I k prime prime, or which is 0 I, in this case n2 k sin theta 2x plus cosine theta 2y. And then now the thinking about the momentum conservation as the interface, meaning that this can be decomposed into the x component and y component. So when we think about the momentum conservation in the x direction, it can give n1k n1k sin theta 1 equal n2 k sin theta 2, which just gives a Snell's law, right? But now thinking about the conservation in the y direction too. So in the case of y direction, n1k cosine theta 1 equal n2k cosine theta 2. And you can solve the cosine theta 2 as the cosine theta 2 is, of course, the minus sine theta 2 squared. And these are some kind of strange things happen in this case, because in the case of total reflection, sine theta 2 has reached already kind of like 1, because the theta 2 is now larger than pi over 2. So just assume this one sine theta 2, whatever it is, it's larger than let's assume it's larger than 1. So in this case, we can write like I sine theta 2 squared minus 1. And by using the Snell's law, it can be written like not much space, but like n2 over n1 sine theta 1 squared minus 1. So now all the values you can put in here. So now what it's kind of a little bit strange, because the cosine theta 2 is now imaginary value. And what is imaginary value of the cosine theta 2? And it can be a little bit clearer if you think about the field of E prime prime. So you can E prime prime can be written like I will write this here. So E prime prime equal E0 exponential I and 2k I. Now this cosine theta 2 has an I, so imaginary value. That's why squared minus 1 y. So there's a I squared value, so it's going to from the imaginary part to the real value, and it's kind of decaying electric field onto k. So just same and y. So what I did is it's kind of like a decaying exponential when we think about the E field in the y direction, right? Because already we are thinking about in the case of total refraction, the electric field itself is not going into the minus y direction, but actually there's an exponentially decaying y component is here. So this equation means that E prime prime in the y field, negative y field is decaying part. So this indicates when the light is totally refracted, still the light field can penetrate into somehow. So this field can be written like minus y, but d, and you can calculate d from this value. So this is value. So inverse of this value corresponding to d. And this depth is called the penetration depth. And this field not propagating into, but there's some field going into the lower refractive index side in the case of the total refraction, which is a evanescent wave. Or sometimes it is called a near field, optical near field, this field. And in many cases, when you use the visible light, it's on the order of hundreds of nanometers. And this small confined region of light can be utilized for spectroscopy. And here's one of the example I want to show is the total reflection fluorescence microscope. So where this one is the objective lens, and intentionally light is illuminated from the side of the objective lens, and then with a very large angle of incidence to the sample. That's why the light is totally refracted. But thinking about this one, even if the light is totally refracted, the light field can penetrate into the sample only 100 nanometers. So you can obtain the information at the very surface region of the sample. Okay, so that's it.